So I chose a pretty provocative title today saying, forget about emergence. And I'm going to try to convince you that it's actually a good idea to forget about emergence and to forget about reductionism too and see what we're left with. Okay, so I've got to point it to, nope, doesn't work at all. Worked a few minutes ago. There we go. So we're going to start with a little poll. How many of you have ever heard of quantum computing? Raise your hand. Not know anything about it, just have you heard of it? So it looks like at least a fair number of you have. How many of you have ever heard that quantum computing is a lot faster than ordinary computing? So, whoever figures out quantum computing is going to be able to wreck all of our financial transactions and all of that, put our banks in trouble, and sort out the Defense Department and so on. Okay, so today's questions are, what's the difference between classical computing and quantum computing? And then we're going to segue from that into what does this tell us about perception, human perception and perception in general. And then we're going to talk about what happens when we just forget about these concepts of emergence and reduction. What are we left with in studying perception? So let's talk about quantum computing. But first I want to put one assumption on the table. I'm going to assume that, basically I'm going to assume that quantum theory is a correct description of the world. But what I'm really assuming is that two symmetries of quantum theory are correct descriptions of the world. And I'll talk about each of those symmetries as we go through this. And I suspect that we can get quantum theory from those two symmetries and nothing else. No other assumptions. Okay. Okay. So we're going with a different clicker now. Okay, well, as long as I have the laser pointer, I'm fine. I can click with that. That's no problem. Yeah, this still works. Brilliant. Okay. Just means I have to wear glasses. So keep in mind, though, that this is an assumption. And if it turns out that these symmetries are violated for real in the world, then everything I'm going to tell you today is wrong. Because it's all based on the assumption that the symmetries of quantum mechanics actually hold. So this is a very deep, as Don was mentioning in his case, a very deep empirical assumption is that the universe has the particular symmetries we'll be talking about. So, let's talk about quantum computing. Well, now actually no methods of advancing the slides work.
I don't know where you were.
Let's go a little bit farther. Okay, there we go. All right.
Now it should work.
Now it should work. Okay, great. Thank you very much for the rescue. Okay, so let's talk about quantum computing. Quantum computing is really very simple. And this is the simplest possible representation. There are many, many representations of quantum computing. They're all provably identical. So it doesn't matter which one we talk about. So we're going to talk about this one, which is simple. The simple version of quantum computing is you start with a question, and a unitary process is executed, and you get an answer. This is called the Hamiltonian oracle view. It's the model of quantum computing that David Deutsch used to design the quantum Turing machine model. It's provably complete. So anything you can do with a quantum computer designed any way in the world, you can do this way. So the heart of this is this thing I've called a unitary process. And unitary processes are actually the heart of quantum mechanics. So this is what a unitary process is. It's a process that you can reverse and get the identity. So the way to think about this dynamically is a unitary process is a process that is perfectly time symmetric. So this is symmetry number one of quantum theory. Quantum theory is perfectly time symmetric. Evolution is unitary. And I would claim that if you think hard about what time symmetry means, you will understand quantum theory in an intuitive way. But you have to really think about time symmetry because it's something that's radically unlike what our world is, typically. And we'll see some of the ways in which it's radically unlike what our world typically is. So time symmetry in particular means causal symmetry. So we have a question, we have an answer, and in a symmetric unitary process, you can think of it as a combination of a forward process that goes from the question to the answer and a reverse process that starts with the answer and goes back to the question. And in fact, there's a beautiful series of papers by Giuseppe Castiglioni, Castagnoli, in Italy. And he has shown that if you think of a quantum computation in this way, as starting simultaneously at the question and the answer and working toward the middle and ending with the two processes hit, like the golden spike in the railway, then you can completely understand the speed up of quantum computation over classical computation. And the way he puts it is that a quantum computation always knows half of the answer up front because it's working at the same time from the answer backwards in time. And there's a very nice treatment of this in Ruth Kastner's book, The Transactional Interpretation of Quantum Mechanics, which adds some other stuff that I think is probably not quite right, but she does a nice treatment of time symmetry in this forward and reverse way. However, there's a problem with this picture. And you all have probably already sorted out what the problem is. The problem is that these words question and answer are not time-symmetric words in our vocabulary, right? You ask the question first, and then you get an answer. It's not, we don't think of that in a time-symmetric way. So the problem is that we've taken some informational concepts, question and answer, and we've defined quantum computing by mixing these up with unitary evolution, which is a purely physical concept that has to do with time symmetry. And so we've got to say how these match up, to have a theory that actually means anything. Technically, the last picture I showed you is completely meaningless. So let's fix that by making explicit that the unitary process acts on some physical states, some states in the world that are subject to dynamics. But question and answer are semantic concepts. So what we've done, and I want to emphasize the we here, some observer has interpreted this physical stuff going on in terms of a question and an answer. Now that's a semantic process. That's giving something meaning. So we've constructed a map, a semantic map, from something down here in dynamics world to something up here in semantics world. And that's what allows us to talk about problem solving. We interpret something going on in the world as a question, and then we interpret something going on in the world as an answer, and something or other has happened in the middle, which we may or may not know how to interpret or how to measure or anything else. But we know how to do something very important. We know how to say, I'm going to ask a question, and get an answer, and then I'm going to use the answer to be in my next question and get another answer and get another answer. So we know how to iterate this process. And when you iterate this process, you get a whole chain of events up here, all of which are semantics, that sort of ride on top of this dynamics down here that you may have no characterization of at all. But, and here's the second symmetry of quantum theory, your interpretation up here, the semantics, what you call things, doesn't change the dynamics. That's an assumption. It's a very important assumption because without that assumption, we can't do science at all. If what I call this lectern, if I call this a Blidget, it doesn't change the laws of physics. If it did, science would be impossible. Every language would lead to not just an impression of different laws of physics, but actual different behavior of the world. So we have to assume that's not the case. That's sort of the most rudimentary assumption of communicative objectivity that you can make, that semantics doesn't change the physics. That means there's no such thing as physical collapse. So you've all heard of collapse of the wave function. Doesn't exist. And I'll show you why. And if you're not convinced by the end of the talk, ask questions in the question period. So what are these induced mappings up here? From question 1 to question 2 to answer number 2 here. That's just Turing computation. That's exactly what a Turing machine is. It's just turning one symbol into another, where the symbols are semantic interpretations of something or other going on in the world. So, for example, we can interpret some state of the world as that equation and do an operation called addition and get that representation and then multiply and get that representation. We're just manipulating symbols. But this stuff down on the bottom, all this physics, that's going on in your laptop or your head or somewhere. Okay, so what have we learned here? We've learned that classical computation is just a semantic interpretation of something going on in the world that's describable by quantum theory. So, in particular, this thing is a quantum computer. Your iPhone is a quantum computer. They're quantum computers that are carefully designed so that you don't realize it. So that you can treat them as perfectly classical devices that behave in reproducible ways. The thing is a quantum system. I mean, on the inside, it's just a bunch of energy and stuff moving around. Okay? So, forget about the difference between classical and quantum computation. It doesn't exist at the physical level. So here's an example, right? This thing is a bunch of energy. And if I look at it at kind of a small scale, I see that. That's the inside of a central processor of a computer. Now, when I was a graduate student, we had a computer called a PDP-9 in our lab. It was about the size of 6 or 7 refrigerators. If you opened up the back doors, it looked just like that. But you had to go in there and move the wires around sometimes. And in the 50s, all programming was done by moving wires around. So that right there was the user interface. It was just, twice as big as this area right here. Now we have user interfaces that look like that. And I think I'm dealing with PowerPoint and Linux and, a page viewer or something like that. All of that's just a fiction, like Don talked about this morning. It's just software. But this stuff is just software too, right? We defined this. This is something that we configured the physical world to make it easy to manipulate for us. And we said that's a device, but it's really just a user interface. It's an interpretation of what's going on. So we can generalize this and say any classical computation is a user interface on a quantum computer, and in fact, all classical symbols of all kinds, all of language is a user interface. So we're done with the first part. I want to emphasize that I've done nothing fancy here at all. This is old stuff from textbooks. This is just standard denotational semantics, which is the techniques that one uses to define programming languages. And it's been around forever. It all rests on a paper that Alfred Tarski published in a philosophy journal, Philosophy and Phenomenological Research, back in the 40s, when he first developed the theory of how to do the semantics of formal languages expressed in logical notation. So this is ancient standard stuff. And I want to emphasize, nowhere in this talk am I doing anything weird or new. Okay, so what does this mean for perception? So let's look at the usual picture here. Usual picture is something happens in the world, and someone sees it or detects it somehow or other, and they have an experience, and maybe they do something. Maybe there's some behavior. So this perceiver here is obviously a little bit concerned about what they saw. So we want to look at this process. So let's slow time down a little bit. Look at what happens, okay? So there's an event, and then some information travels through space, and it whacks the perceiver, and it causes an experience, and then the experience causes a response on the perceiver's part. So this is all very classical. So let's look at this again, and think of how classical this is. Something happens in space and time. Information moves at a finite speed, right? The speed of light or less. It causally impacts the perceiver and causes an experience, and then the perceiver reacts. Now, note, that is not time symmetric. I have not given you a quantum mechanical description. This is as classical as the day is long. So let's put this in quantum theory terms. Here's the quantum picture of the same thing. There's an initial state of the world in which we have an event and a perceiver. And the perceiver hasn't noticed the event yet. That's just a snapshot of the world. Let's call that the initial state. And there's a process that acts on this entire system to produce some final state, which consists of the perceiver, their experience, their reaction, and if the event is still happening, it's still there. Maybe it's gone away. But this whole thing turns into that whole thing by a unitary process. And remember, these things are processes that are time symmetric, and they're independent of how we describe them. Two symmetries. So what's happening here physically? Physically, we say that some event coupled to some observer evolves through time to some event coupled to some observer just at a different time. So I'm writing these things coupled together, that's what that cross with the little circle means, to say this is all one thing. It's all evolving together in time, okay? And it works both ways. Now, this is what's physically going on. What's the result? The result is that this event gets classically correlated with the experience. That's what we used to say by cause. But there's a correlation now between the event and the experience, or in information theoretic terms, the observer now has information about the event. Okay? So there's a word for this in quantum theory. It's entanglement. There's a physical process going on in an entangled state with a bunch of components, and that process, as a result, classically correlates two components of that state. So, how many of you have heard of entanglement? Most of you. How many of you have heard that entanglement has something to do with faster than light communication? Okay, you're all in good company because, of course, Einstein himself gave you that interpretation back in his famous paper in the 30s. And if you think about entanglement this way, you will never understand it, ever. So here's the definition. Entangled in quantum theory just means not separable. That's all it means. And not separable means this. It means you cannot equate the state of an entangled state with a bunch of components. You cannot equate it to some mixture of the states of the individual components. You can't say this thing is A and B interacting. That's wrong. So read not equals as, if I think about it this way, I will get it wrong every time. Okay? So what entanglement means is one physical system with one state. So whenever you hear, I have two entangled photons, right? That's wrong. That's crazy. You don't have two entangled photons. You've got one physical system with two photons as components. They're not interacting at all. They're just an entangled system. So let's think about this. Let's look at the standard Nicholas Geisen type experiment. And I picked Geisen because he did this kind of experiment first over a separation of about 10 kilometers about 10 years ago in Geneva. And the most recent paper I've seen, which was just 1310, so that's this month, was from a Japanese group who've done the same experiment over 300 kilometers. So next time someone says quantum mechanics, that's just about little bitty stuff, okay? Remember when you thought cells were little bitty things, and then someone said, oh, you've got meter-long cells in your legs. You said, oh, wait, cells are big, like that. So quantum systems are big, like 300 kilometers long. So quantum mechanics is not a microscopic phenomenon. It's a macroscopic phenomenon. 300 kilometers is big. So what happens in an experiment like this? You've got a source, and the source emits an entangled state of something. So maybe it's an entangled state of two photons, two electrons. You know, in reality, most of these experiments are done with photons. So the photons come out, and they're coupled in the spin coordinate. So one of them spin up and one spin down, typically. Easy to make, okay? They move apart, and there are two observers. And the observers are always called Alice and Bob, because it's more fun than calling them A and B, okay? So Alice and Bob have detectors, and they're separated in space by a long way. And the photons, if you think about it, if the photons are coming from this source toward Alice and Bob, they're going to get to Alice and Bob in the same amount of time or less than it would take for Alice or Bob to send a message to each other. And they'll get there in half the time for Alice to send a message to Bob and Bob to send a message back. Okay? Hence the faster than light confusion. So what's going on here? The photons come out of the source, and everything inside is entangled, right? The whole system moves as one. And the light moves a little bit more, it's still entangled. A little bit more, still entangled. And then suddenly Alice and Bob get a signal. They say, up, down. Okay, now they know they've observed an entangled state. But it was entangled all along, right? What Alice and Bob know is absolutely irrelevant to the physics. That's the symmetry. What we call it doesn't matter, okay? So here's the message of entanglement. This is what quantum mechanics has been trying to tell us for 80 years, and we're like this, okay? We don't want to hear it, right? It's trying to tell us there are no boundaries. The universe is an entangled system. There's just one thing, and it evolves through time, in quotation marks now, as one single system. Now, physicists hate this. Why? I mean, this is what quantum mechanics is telling us. Why is it a problem? It's a problem because it makes it very, very hard to say what an experiment is. Right? A physicist wants to say, okay, we're going to manipulate the world somehow or other and see what happens. But if the whole thing moves as one, there's no manipulation going on. And, you know, physicists are little bitty things, and the rest of the universe is a really big thing. So if anything at all is going on in experiments, nature is manipulating us, right? Us manipulating nature, that's nonsense. It's crazy. It's silly, right? Nature manipulates us when we do an experiment. And physicists call this conspiracy, that nature is only going to reveal what she wants to. Well, of course, okay? But there's a lovely article by Gerardus de Hooft a couple of months ago, again on the archive, it's not published yet. And in this article, he basically says, conspiracy's just the way it is, gang, get used to it. And he has a Nobel Prize, so he's much, much smarter than I am. But that's the message at any rate, and it's good that it's being said by people who are taken seriously. So let's do Geisen's experiment again, keeping in mind that everything is one quantum state, so it's entangled, still entangled, still entangled, still entangled, and this business of knowledge is irrelevant. Alice and Bob don't know they're entangled for a long time, but they're entangled through the entire process. Okay, so here's our result. Entanglement is how classical information is transferred from one place to another. So entanglement is what implements perception. It's the one mechanism we have within quantum mechanics to implement perception. And it implements it all the time. It says, okay, this thing over here is entangled with that thing over there, so we'll exchange some classical information. And note that that's relative. It's always relative to the specification of a coordinate system. And by the way, this perceiver-perceived boundary, there's no boundaries in physics, so that boundary is just semantics, including my boundary with you, your boundary with your chair, all that's semantics. Okay, so let's put this all together. Almost done with the second third of the talk. So all reportable experiences, the things we can talk about, write down, make a movie about, store in a disk drive, anything we can report, put it in a memory and expect to stay the same. All reportable experiences are included in classical information. That's what classical information is, stuff you can put in a memory. All classical information is semantics. It's just a user interface on what's going on, or dynamics, physics, whatever you want to call it. We're classically correlated with the world, so we can get information, we can learn something by entanglement. And the boundaries that separate the us from the world are just part of our user interface. So I want to reference Don here because he's been saying this for a long time. But we've at least come to it this way by a different route that's complementary to his. Okay, so there's an epistemic bottom line here. It says all reportable knowledge, all knowledge that we can tell someone about or write down somewhere, or even just remember from one moment to the next. Even just remembering something from one moment to the next is making a semantic assumption that your memory now is the same thing that it was when you encoded that piece of information a moment ago. Do you have any evidence for that? No one does, so don't say yes. There is no evidence for that, and there's no way to ever get any evidence for that. So it's just an assumption. That's why it's semantics. So all reportable knowledge is both contextual, depends on the specification of some coordinate system that lets us talk about entanglement, and it's relational. It's about my relation to something I'm entangled with. So knowledge is of the form if X, then Y. There's no such thing as knowledge of the form X, blanket statement. All knowledge is implication or assumption. Okay, so that's all nice philosophy, so what? Well, I'll argue that there are three so whats. Okay? So here's so what number one. This makes a powerful empirical prediction. And this is, in fact, the prediction that quantum theory has been trying to get us to take seriously for 80 years. It's entanglement is everywhere. Every experiment at any scale that's designed well enough should detect entanglement. So it's no surprise that over the last 5 years, we've been getting more and more and more evidence that you can only understand human cognition in quantum mechanical terms. And there are now dozens of beautiful experiments, but the simple one, which you may have heard of, is the pet fish experiment. How many people have heard of the pet fish experiment? Okay, pet fish experiment goes like this. I say, imagine a pet. Okay, so everybody imagine a pet. How many, raise your hand if you imagine Guppy. Nada. Okay. Now, forgetting about that question, which I know you can't do, imagine a fish. Just the prototypical fish. How many of you imagine Guppy? 1, 2, all right? So, now imagine a pet fish. How many guppies? Lots. Okay? Now, classical probability theory tells us the probability of event A times the probability of event B is the probability of event AB combined. Well, we just did an experiment where we had a really low probability of saying a pet is a guppy, and a pretty low probability of saying a fish is a guppy, and a really high probability of saying a pet fish is a guppy. So we've all in this room just violated classical probability theory. Now, it turns out that you can describe that kind of experiment beautifully using the mathematics of quantum theory. And you've just created an entangled state. And now there are now experiments over and over and over and over again showing this in different domains, and the math is getting better, and more concepts are being brought in, like entanglement. And people are getting braver to some extent to say, look, we're seeing quantum mechanical effects going on in human cognition. So I would predict, and Schrodinger could have predicted, and I think he did actually, in at least some of his writings, that we'll see that everywhere. 50 years we'll say classical probability, that doesn't work anywhere. Okay? So that's the empirical prediction. There's a methodological prediction, which is there aren't any parts. So if you go around saying the whole is more than the sum of the parts, well, there aren't any parts. So you're not saying anything. So the whole emergence paradigm is out the window. Forget about that. But of course, if you go around saying, well, we can explain everything in terms of what the parts are doing, well, there are not any parts. So the whole reductionist paradigm is out the window too. So we need to forget about most philosophy of science, which is either emergentist or reductionist. It's just wrong. I mean, if quantum theory is right, it's wrong. If quantum theory is wrong, maybe it's right. But we know that if quantum theory is right, that whole kind of thinking is confused. So if we're going to understand experience then, and we can't use emergence, and we can't use reduction, but none of us want to use reduction anyway, but if we can't use emergence, we've got to study entanglement. And by this, I mean, don't just think about it. I mean, it's good to think about it, but we need to do experiments where we try to understand how human beings are actually coupled to the world in quantum mechanical terms. We've got a good understanding of that in classical terms, but we don't understand it in quantum mechanical terms at all. And so there's a huge new frontier of experimental science, and there are going to be experiments that are hard. Because what's nice about classical science is that you can reproducibly create the same conditions over and over and over again. Quantum theory tells you that's impossible. You're never reproducibly creating the same conditions over and over again. So you've got to be really creative to create conditions that you can pretend are the same and get away with it. And when they're doing those experiments, very near absolute zero in fiber optics and all of that, they can pretend that they're reproducibly creating the same conditions and get away with it. And come up with pretty good evidence that they're getting away with it. But it's harder in psychology. But it's something we've got to figure out how to do. So finally, so what number 3 is kind of the moral or maybe spiritual, but I regard it as a moral point, that observers are everywhere. So that's an observer. The system that consists of my big toe and my glasses is an observer. The black hole in the middle of the Milky Way is an observer. So there are observers everywhere, at every scale, and most of their experiences are nothing whatsoever like ours. So you have your experience. Think about the black hole in the middle of the Milky Way. What's its experience like? You're probably saying, who knows? Well, we don't know. We don't have a clue. But we can assume pretty clearly that it's nothing like our experience. And I think what that gives us is a certain amount of humility, to think that our experiential position in the universe is not privileged in the least. There's nothing special about being us. There are lots of other systems out there that have a rich experiential life. They're nothing like we are, and their opinions of things are probably radically different from ours. So, with that, I'm done. Questions?
Thank you very much, Chris. Elizabeth Rauscher and I have been talking about the possibility of putting a Josephson junction in a mu metal shield and then having a second virtually identical, hopefully, Josephson junction that then can be modulated as you would a radio wave or a television broadcast, and to see whether under superconducting conditions, whether this already entangled state of all observers would allow for information transfer that could be considered to be instantaneous, so that we could do without radiomagnetic transmissions.
I would guess that you won't transfer classical information that way. You'll transfer plenty of quantum information that way. I know you want to transfer classical information.
Could you make that distinction more clear? Yeah. Like, can we transfer useful information?
Well, I think that's a different dimension. I mean, at a physical level, all the information that we use is quantum information. So it's useful to the extent that we've survived and can do things. But the information that we write down in memories and assume is going to stay the same. So in a sense, all the information that we think of as cultural is classical by definition. Now, the question is, what's the interpretive process that allows you to say that a piece of information is classical? It involves making an assumption about its existence over time. And it's an assumption that we don't understand very well. And we understand something about how the brain executes the process of making that assumption. That, I'm the same object that I was 5 minutes ago. You've probably all assumed that. But, no evidence in the world that says that that's true. It's something that we make up. And so your question goes to that core semantic issue of what does it mean to say that I've gotten a useful piece of classical information from point A to point B? And it's a very familiar question in quantum computing, because it's exactly the question I define some state of a quantum computer as an input, and then I wait a while, go have a cup of coffee, come back, and the quantum computer's in another state. So is that state that it's now in, the two factors of some, 10 to the 97th digit prime number? Well, I can find out in that case by multiplying the answers together and see if it's what I defined to be the initial state. But in most cases, we can't do that. We have no idea how to do the semantics of quantum processes. If there's no such thing as time, I have no idea what the word travel means.
We are coming to the end of our time. We can keep going because we have a panel on which you are on coming up. If the people that are setting up the panel want to do that while you're talking, if you want to keep taking questions, we can do that.
Okay,
Yeah.
we can have other questions if we want.
All right.
Thank you, Chris. A question from a classical psychologist as opposed to a physicist then. Your little guppy example, if I look at that from the point of view of, let's say, a social psychologist, what you did was bias your respondents by contextualizing in the information that you provided us in your questions. So in a sense, you biased us toward a certain set of responses. Can you reinterpret that in entanglement terms?
Yeah, contextuality is almost another word for entanglement. And in actually the results within quantum theory that illustrate the effect of entanglement on supposedly independent experimental processes are actually called contextuality results in analog with what you see in psychology. So I suspect that a lot of classic psychological data can actually be reinterpreted in quantum theoretic terms, and these sorts of effects, many of which we understand to some extent mechanistically in terms of what's going on in the brain, we can say, okay, this is a case that actually illustrates quantum statistics in action. I mean, there wouldn't be contextuality if we lived in a perfectly classical world.
We have another question back here.
Could you elaborate on the point you made that observers are everywhere and what impact that has? I didn't quite follow what that means in practical terms.
Okay. That's why I characterize it as a moral point, because we tend to think of ourselves and maybe mammals and maybe trees as observers. But we don't think of computers as observers, or chairs as observers, or planets as observers, for example. But if you think of observation as information transfer, and you think of information transfer in physical terms, then it becomes very difficult to say what's different between information transfer in my case and information transfer in a thermostat's case, to take the classic silly example that philosophers use. They say, well, surely you can't be a panpsychist, because then you'd think that thermostats made decisions. And in my opinion, the right response to that is say, yeah. And there's a wonderful paper by Christopher Fuchs, who's the guy who kind of invented quantum Bayesianism. He's a quantum computation, quantum information guy. And he says in this paper, with reference to something called the free will theorem, that does his theory actually imply that elementary particles are making decisions? And he says, yeah, it does. That's just get used to it.